Hi, in this video we'll talk about inverse functions. Inverse functions are very important because they help us solve equations. Without them we can't solve any type of equation. Essentially what an inverse function does is that it undoes another function. Let me explain. Let's say that we have a function f, and I have another function g, and we'll do a composition like we did in the last video. Okay, so I get an x, I plug it into f. That gives me an f of x. And imagine that g is just that perfect function so that when you feed it the f of x, it returns x. Okay? It goes back to that very original input. So if we were to do the composition of those two functions, we would see that, that g of f of x is x. Okay? Or equivalently, that g of f of x is x. Okay? So whatever complicated thing f does to our input x, scrambles it all up, g will unscramble that. And not only that, it won't just do it for one particular input value, it'll do it for all the input values. Not only that, imagine if we change the order of these two functions, and we still get this super nice property that no matter what input we feed into into g scrambles it all up and gives us some sort of weird output. F finds a way to figure out the original input. Okay. So here, our x returns to our x. So we have f of g of x is x. Or equivalently, f of g of x is x. Now, if we can find a pair of functions like that, well, then we say that those functions are inverses of each other. Okay? And we use this notation. We would say that they have such a special relationship that g is equal to, and we use this weird notation, f and a superscript minus 1. Or we would write f is g superscript minus 1. It is not an exponent, however. Even though it really looks like it, it is not to be thought of as an exponent. Now, in order for this all to work, we need that the domain of f has to be the range of g, and the domain of g has to be the range of f. So that has to perfectly fit together. Kind of what we're doing is that if we think of f taking a certain x value and producing a y value, then what g does is it swaps that. It takes a y value and gives you back the x value. Okay? So inverse functions, when you look at them, they're swapping the x and y values. So if we're swapping the domain and range, that makes a lot of sense. Also, we'll see later on that if we draw the graphs, if we just swap the order of the coordinates of a point, we get a point on the inverse function. But before I get too far ahead of myself, let's practice a little bit with these inverse functions. Let's assume I've got some mystery function f, and it has an inverse. I don't really know what the inverse function is, and I really don't know much about f other than a couple of its function values. Now, if I want to figure out what f inverse of negative 3 is, what I want to do is look through this list until I find a y value that's negative 3. There it is. And what's the x value that gives me a y value of negative 3? 3. So that means that f inverse of negative 3 is 3. Since f of 3 is negative 3. So if we have an xy for f, then on f inverse, we're just going to change the order of those coordinates. Okay. If I look for f inverse of 0, I just need to hunt through all my outputs of f to find one that is 0. There it is. And that means that f inverse of 0 is going to be negative 2. Since f of negative 2 is 0. We're trying to do things backwards here. I'm trying to ask myself, what x value would I plug into f to get an output of 0, to get a y value of 0. Okay? Now, if we take a look at the next one, we could figure out f inverse of 2. That's on the middle, on the inside here. So f inverse of 2, if we look above, which one has a y value of 2? There it is right there. So f inverse of 2 would have to be negative 3. And then if I plug negative 3 into f, wait, that's talking about the exact same little piece of information there. It would have to be 2. So if we think about it a minute and think of the definition of a function and its inverse, notice that I'm taking f inverse of 2 and immediately plugging it back into f. So we have those two happening one right after the other. One is changing 2 into negative 3, and the other one's changing it back into 2. We know that fundamental property that f of f inverse of x is always going to equal x. So we might have been able to jump straight to the final answer. Okay? So if I look at the next one, look, we've got f inverse of f of negative 1. Well, that's also a property of inverse functions. So I don't even have to look above. I know the answer is going to be negative 1. Okay? But for number 5 here, we don't get that nice property. Okay? Notice it's not f and its inverse, it's two inverses. So we have to do this step by step. Now f inverse of 2, well, we calculated that actually just above, so I'm just going to reuse this idea here. It's going to be negative 3, so I'm looking at f inverse of negative 3. And now f inverse of negative 3, I want to find out what x value, when I plug it into f, gives me a y value of negative 3. Oh, actually, I guess we've done that one before too. Okay, there's f inverse of negative 3. Turns out it's 3. All right, so that's how we can calculate inverse function values. We're essentially swapping the x's and y's. Now, next let's take a look at how to graph inverse functions if we know the graph of the original function. So say I know the graph of y equals f of x. Can I then figure out how to draw y equals f inverse of x? So let's actually take a look here at this one. Okay, we know how to draw this exponential function. It's telling us about exponential growth since the base there is bigger than 1. So I'm just going to draw y equals 2 to the x. There we are. It's one of our prototypes. Okay. Now, if I want to draw the inverse function, it's going to swap all the x's and y's. So I think of all the points on the blue graph. If we think of a point like 0, 1, it's going to become, or in the inverse graph, 1, 0. So I'm going to have that point down there. And if we think of the domain of the blue graph is all real numbers, that means the range of our inverse function will be all real numbers. Okay. Also, we notice we've got a horizontal asymptote on the x-axis. That means the y-axis will be a vertical asymptote for our inverse graph. Stronger than that, even, if we draw the line y equals x, all our inverse function graph is going to be is a reflection of the blue graph about that diagonal line. So I'll try to draw it as best I can here. And so that's the inverse function. If f of x is equal to 2 to the x, then this would be y equals f inverse of x. Okay. Now we're going to study these particular functions later on because they're very important. They unlock exponential functions. And for those of you who already know about them, they're logarithmic functions. Now notice all the symmetry that's going on. The x-intercept on the blue graph is related or corresponds to the x-intercept on the green graph. The Vertical asymptote on the green graph corresponds to a horizontal asymptote on the blue graph. The range of the blue graph is all positive real numbers. That's also the domain of the green graph. There's this symmetry back and forth. Let's try another example here. Let's take a look at y equals x squared, but we're going to restrict ourselves to x being greater than or equal to 0. What does it mean to restrict the domain like that? Well, it's the parabola prototype, except I'm only going to have non-negative x values. So there we have it. If I want to draw the graph of the inverse function, I'll draw in the line y equals x, that diagonal line, and I will reflect my blue graph about it. Now, do you recognize that curve? I hope you do. We're going to be talking about it later this week. Okay? Turns out that's y equals the square root of x. And that makes a lot of sense. What function undoes squaring something? Well, square rooting it. And what function undoes square rooting something? Well, squaring it. Okay? Those two functions undo each other. They're inverses of each other. I'll let you try the number 4 here on your own, as well as the other missing one on the last page. Now let's talk about how we can actually find the equation of the inverse function. We can do this sometimes. So, as I've been saying about inverse functions, what are they doing? Compared to the original function, they're swapping x and y. So that tells us exactly what we should do to find an algebraic description or an equation for the inverse function. We're going to swap x and y. So if I look at this first example here, I'm going to take x equals 3y minus 5. I'm swapping x and y there. And then I'm going to isolate y. So I'll bring it over to the left, my term involving y, bring my term involving x over to the right, and isolate the y. Okay? So that means that f inverse of x is also a linear function, but has a different slope and a different y-intercept. Okay? How about number 3 down here? Let's take a look at that. If we swap x and y, we get this. And if we try to isolate y, well, I'll kind of do some cross multiplication here, or we'll bring up that denominator. And then to continue to isolate the y, we'll divide both sides by x. I'll subtract 4 from both sides. Just peeling away all the layers one at a time until I can get at the y there, starting with the outermost layers. And then we've got, finally, a division by 2. So there we have it. We saw that our original function was a certain rational function. Our final one is also a rational function, our inverse, but very different rational functions. So that's how we can find the equation of the inverse function. So what you need to remember about all of this is when we have two functions that are inverses of each other, in a sense all they're doing is swapping the roles of x and y. For the function itself, what it means is inputs become outputs. For the graphs, what it means is that we reflected about the line y equals x. And if we want to find the equation, what it means is that we're going to swap x and y and then isolate the new y. In the next video, we'll talk about those radical functions that we saw in the previous picture and as our first example of an inverse function. Thank you.